In the previous video, we talked about how the ATP molecule is often coupled with endergonic and exergonic reactions as a way to capture energy, move it to a different location within the cell, and then use that energy to power other chemical reactions. ATP is not the only molecule that does this, and it's also not the only type of chemical reaction that this occurs with. What I'd like to focus on now is another very common type of chemical reaction coupling that is used to move energy around the cells. These are called redox reactions. Redox reactions come in two forms, oxidation and reduction. And redox reactions are all about moving electrons. Electrons, E-, are negatively charged ions. Now, an electron is an energy source. It contains energy, and that energy can be used to power things in the cell. When molecules gain extra electrons, so when they gain electrons, they are what we call reduced. They've been reduced, and they contain more energy than before they gain those electrons. At the same time, when they lose an electron, they have been oxidized. They've been oxidized, and they are at a lower energy state than they were when they had the extra electrons. So oxidation and reduction reactions, called redox for short, reduction and oxidation, are a very common way to move energy around the cells by passing electrons around. Now, one of the challenges, of course, is trying to remember which one's which. And there's a mnemonic to help you with this. Leo the lion says grr. You can see I've written it down here. Leo stands for loss of electrons is oxidation. And grr stands for gain of electrons equals reduction. Another way to remember these, and this is what I tend to go with, is math. Reduction means to get smaller, and I think electrons are negatively charged. Well, if I take a number, for example, 3, and I add a negative value to it, so a -1, I end up with 2. I have reduced the value of my original thing. Well, if I add a negatively charged electron, I've reduced it because I've made it more negative, and therefore that is a reduction. You might come up with your own method of remembering these, but it is really important to remember oxidation and reduction reactions. One of them is about gaining extra electrons, and the other one is about losing electrons, as these electrons are moved around and energy is shifted from one molecule to another. So let's take a look at how this actually works. Oxidation and reduction reactions are always coupled. You can't take electrons away from a molecule without putting them somewhere else. And so anytime oxidation occurs, reduction also happens to occur. So let's take a look up here in my diagram. I'm going to start off, I have two molecules. I have molecule A, and I have NAD+. Okay? It doesn't matter what the name of molecule A is. It could be anything. It could be glucose. It could be some other molecule. It doesn't make a difference. It's just molecule A for right now. And if you look, what's happening here, A, and it has an H attached to it, hydrogen. We're going down here and follow along, and we're losing the hydrogen. The hydrogen's going away, so we just have molecule A at the end of this. At the same time, NAD+ is coming here. The two molecules are reacting with each other, and we end up with NADH. So basically, we took this hydrogen, and we moved it from one molecule to the next. Now, you might be a little confused at this point, saying, wait a minute, I thought oxidation and reduction was about moving electrons, and here we are showing the movement of hydrogens. Well, you're not wrong. The reason we do that is chemical reactions don't generally show electrons. They instead show the different elements that make up molecules. And in this case, hydrogen is the element that we're going to follow. Well, it just happens to be that hydrogen and electrons tend to move together. So in redox reactions, oxidation reduction reactions, we tend to follow the hydrogens with the understanding that the electrons are also moving with the hydrogens. So if I go ahead and erase this for a second, what we are saying is going on in this case is my A molecule is passing electrons from the A molecule over to the NADH. And the way we know that's happening is because hydrogen moves with the electrons and is shifted from one molecule to the next. When this occurs, my A molecule is being oxidized, is going through an oxidation reaction, it's being oxidized, it has lost electrons. My NAD plus molecule, meanwhile, is being reduced. It is going through a reduction reaction and ending up NADH, which has gained electrons in hydrogen. Okay. So this is how oxidation reduction reactions happen. They couple an oxidation, losing electrons, with a reduction reaction, gaining electrons. The electrons have to go somewhere, so you need both of them to occur. Okay, let me clean this up a little bit. Now, I want to talk about a very particular molecule that you're going to see repeatedly as we start getting into cellular respiration. And that's the NAD plus NADH molecule. This is the same molecule. So NAD plus and NADH. Same molecule. The difference is the NADH version has been reduced. The NAD plus version is the oxidized version. So NAD plus acts as a taxi cab in these oxidation reactions. NAD plus will be reduced, gaining hydrogens and electrons, and it can then go to another area of the cell, much like what ATP did. It can go to another part of the cell carrying that extra energy in the form of electrons, and then it can provide those to power other chemical reactions. In the diagram above, we see that. We see the A molecule get oxidized, thereby reducing NAD plus into NADH. The NADH then will go to another part of the cell, and it can then be oxidized and reduce a different molecule, molecule B in this case. Molecule B is reduced. It now has the extra energy, power a chemical reaction. NADH goes back to being NAD plus. It has been oxidized, and it can work again. So just like a taxi cab, drops off its passengers, goes and finds new passengers, and does this over and over and over again. NAD plus is a very, very important molecule in these oxidation and reduction reactions, and you're going to see it frequently. So become familiar with it and understand how it works. So now I have one more question for you in this kind of chemical reaction. Clear the area again. What do you think would happen if I got rid of molecule B? If we removed molecule B from this series of chemical reactions, what impact might that have on the rest of the chemical reaction? Go ahead and pause the video just for a second and try to answer that question, and then unpause when you're ready to have me talk about it. Go ahead and pause. Okay, if we remove B, what we are doing, we are removing the reduction reaction that is happening in this coupling. Well, oxidation reduction reactions have to occur together. So I have created a situation where the electrons in NADH have nowhere to go. So they're not going to leave. We have, by turning this reduction reaction off, we have also turned off this oxidation reaction. As a result, we're going to start stockpiling NADH. We're going to get more and more and more and more of it, because this oxidation reduction reaction is still going to occur. NAD plus is still going to be reduced and turned into NADH. AH is going to be oxidized and turned into A. So this process is going to continue. This reaction will continue, this reaction will continue, but this one will stop. Ultimately, what is going to end this chemical reaction? Well, at some point along the way, we're going to run out of NAD pluses, because normally NADH becomes NAD plus again when it's oxidized and can get used over and over. In our taxi cab analogy, this is a point of all the taxis are full and they can't drop anyone else off. Maybe really bad traffic. Okay, so because oxidation reduction reactions are coupled, If you remove one piece from it, not only does it affect the direct oxidation reaction that piece was involved in, but it can affect every previous series of oxidation reduction reactions all the way back to the beginning. That's going to become important when we start talking about cell respiration. Okay, so you'll see that question again in that particular context. For now, this is an oxidation reduction reaction, commonly called redox reactions when they're combined together. And you're going to see these again coming up. So this is a common way, in addition to ATP, the energy is moved around the cell.